Welcome everyone to Unit 7. We're going to be talking about energy, and for the rest of the semester actually we're going to be talking about energy in its various forms. But the form that we'll be talking about mostly today is going to be mechanical energy, and we'll get to that in just a second. What is energy? It's the ability to do work, or the ability to cause a change in a system. And if you look at all these examples, you have electrical energy such as electricity, and chemical energy, gasoline, food, explosions, things like that. Thermal energy, radiant energy, light from the sun, mechanical energy, and nuclear energy. These are all types, different forms that energy can take, but what they all have in common is they can all be used to cause a change in a system. The primary form of energy that we're going to be working with in this unit is mechanical energy. And mechanical energy is comprised of two different types of energy. When you think of the word potential energy, when it comes to potential, kind of means what it says. It's kind of stored energy. It's waiting to be used. At that moment, maybe nothing is going on with it, but it has the ability to do work in the future or to cause a change. Kinetic energy, some of you might have heard the word kinesthetic before, and that's having to do with anything moving. So kinetic energy is dealing with motion, and we talked about potential and kinetic earlier in the semester when we talked about static friction, and kinetic friction and static friction being potential and kinetic. So let's focus on kinetic energy. This is the energy in motion, and it's measured in joules with a capital J. Now that capital J, we've seen that before in our previous unit when we saw impulse. Well, that's only a capital J when it's in a formula. When the capital J follows a number, then it's a unit, and that's the unit for kinetic energy. When you look at the formula for kinetic energy, you probably recognize it's very similar to the momentum formula. Momentum has mass and velocity, and objects that have momentum also have kinetic energy because they also have mass and velocity. But the formula is a little different, but at least you can see the similarities there. The squared right here only applies to the velocity, which we'll see in a moment means that the velocity of the object has much more of an influence on its kinetic energy than the mass does. So let's work a sample problem here. So kinetic energy is equal to 1/2 of the mass times the velocity squared. So in this scenario, this microwave oven, maybe your mom asked you to bring it inside and set it on the counter, and you had a popsicle in your mouth, so you weren't really paying attention. So you set it on the edge, and va-vam, it fell off. Now we said before that the squared here only applies to the velocity. So that's 1/2 times 10 times 16. Only the velocity gets squared. And when we do that, 16 times 10 is 160, and half of that is 80. So that microwave oven had 80 joules of kinetic energy. Well, let's look at what happens if you change some of the quantities involved. All right, so what if you have a microwave oven that's twice as massive? So we can look and see that 4 squared is 16. All right, so we have 16 times 20 is 320, and half of 320 is 160 joules. So it looks like if you multiply the mass by a factor of 2, you end up doubling the kinetic energy. So it's kind of a 1-to-1 ratio. If you increase the mass, you increase the kinetic energy by the same amount. Now let's look at what happens if you change the velocity. So what if we keep the mass the same, so it's still the same microwave oven, but instead of falling off the counter, what if we push it? Okay, so instead of going 4 meters per second, it's now 8. So we have 1/2 times 10 times 64. Okay, so 64 times 10 is 620. And half of 620 is 320 joules. So it looks like if you double the velocity, the kinetic energy goes up by a factor of 4. And that's all because of this little thing right here. That squared really has an influence on the amount of kinetic energy. So the next thing we have here is potential energy. And you can see there's lots of kinds of potential energy. We're going to be focusing on the potential energy that's based on the position, which is this one, the gravitational energy. Gravitational potential energy is what we'll focus on. But there's other kinds like chemical potential energy. When you eat a sandwich, your body uses the bond energy in that food. When you burn gasoline in your car uses the energy in the bonds. So those are examples of chemical potential energy, where we use the energy that holds chemicals together. Elastic potential energy, that's like with a bungee cord, or maybe the springs on a trampoline, or a rubber band. Anything that when you stretch it, you give it potential energy, and then when you release it, it'll be converted back into kinetic. And then finally, you have things like electrical potential energy, like electricity, and then nuclear. So here is our formula for potential energy. Potential energy is also measured in joules. So both kinetic and potential energy are measured in joules. And we see here again that gravity, mass, times gravity times height. So this G is going to be that same G that we used in previous units, and it will be represented with a 10 meters per second squared. Because if you lift something above the ground, if you give it height, and it has mass, there is a gravitational force on it, so you've basically given it stored potential energy based on its position above the ground. So now we'll work a sample problem here. So we have potential energy is equal to mass times gravity times height. Pretty straightforward stuff. The mass is 3, gravity is 10, and the height was 0.68. So we end up getting 20.4 joules. So potential energy basically is the mass and the gravity and the height. So what happens if we double the mass? Well, let's look at what we got here. So we have potential energy. Now we'll say the mass of that boulder was 6. So when you double the mass, it ends up doubling the potential energy. So if you double the mass, then it will double the potential energy. And we'll look at what it does to the height. So if we keep the mass from the previous, gravity is still 10. But now if we double the height, so we multiply that out, and we will get 40.8 joules. So if you double the height at which something is lifted, then that will double the potential energy. So unlike kinetic energy, if you double the velocity, you got 4 times the energy. With potential energy, everything's a direct relationship. One more thing to add is something called the law of conservation of energy. That the energy that you begin with can be transformed into other forms and be converted into other kinds of energy, but it cannot be destroyed. It can be transformed from one form to another, but the total amount of energy never changes. Okay, so to talk about the conservation of energy, we have a little example dealing with a pendulum. And most folks know what a pendulum looks like. So you've got this ball that's hanging on the end of a string, and in the very beginning it's not moving, so it doesn't have any kinetic energy. And it's also at its lowest point, so it doesn't have any potential energy. But then we lift it up. We increase the height of it, and by increasing the height, that gives it potential energy. And so in the very beginning, before we release this pendulum, it's got nothing but potential energy. But as we release it about halfway down, you can see that it's lost some of its potential energy, but it really didn't lose any of it. It's actually now been transformed into kinetic energy. And as you can see, because it's halfway through its motion, it has half as much potential energy as it did before, but it only has half as much kinetic energy as it possibly can have. So half the height means half the potential energy. And at the very bottom of its swing, on its way through, all of that potential energy that it has been completely transformed into kinetic energy. So that's what we mean by the transfer of energy from one form from another. So it started off as potential energy, and then as it's been moving, it's been losing or transforming potential energy into kinetic. But what? Then it goes back up again. And look at what's happening. It's losing or transferring some of its kinetic into potential energy. And I bet you guessed it, when it gets to the top again, it's all potential again. Because now there is no more motion. It's no velocity. No velocity, no kinetic energy. Now it has all height again. So now it has a maximum of potential energy. So what we witnessed with this pendulum is the transferring of energy from one form to another. But the total amount of energy stayed the same. And you can kind of see this with this slide. If you were to take the size of each of the bar graphs and added them together when they were split, you would see that the total amount of energy never changed. So that's what we mean by the energy is conserved.